Alright, so let's go ahead and write our shader. The first thing we're going to do is we're going to duplicate our little tube here and rename this to 2_Lambert. Alright, let's create a new material. This material we're going to call 2_Lambert, a new shader, 2_Lambert, and let's go ahead and write our shader. Alright, so let's just wipe out all of this. We just want to start from scratch, and we're going to do this every time we write a shader. And let's go ahead and create our shader. So shader, and this one here is going to be Unity cookie /beginner, actually /toot/beginner /2-Lambert. So that just creates the folder arrangements for us. So if we come back into Unity and reload this, we can now select it from Unity cookie to beginner to Lambert and drag that onto our model. Now it's pink at the moment because of course we haven't actually written our shader yet, so let's go ahead and do that. So let's go properties, and we're just going to stick to the same as we did before. This will be the color one here. Color equals, and of course we're going to start with a white. Let's create our sub shader, and while we're at it we'll also create a fallback. Alright, so this is all stuff we've been over in the previous one. We have our properties, we're just doing a flat color, our sub shader, and we're just going to have a single pass. And let's go through and start writing our CG program. So here's where things get really cool. I'm going to start off with our pragmas. Let's go pragma vertex vert and fragment frag. We already know that's what we're going to call them, so we might as well write our pragmas out there. Okay, let's start off with the user defined variables. Uniform underscore color, and we need to make sure this is a float for. That way we can define this one here so that we can use it within our CG language. And also we're going to have another one. So this one here is going to be Unity defined variables. So these are variables that we are going to take from Unity itself. So the only one we're going to be using at the moment is going to be the uniform float for underscore light color 0. Alright, so this one here will be the color of the light. So whatever light is affecting this, that's the color that it will get from it. So that's how we can communicate with our light. Now if you are on using Unity 3.5, there's a couple more lines that you need to add in here. You need to have the float 4x4 matrix underscore object to world, the float 4x4 world to object, and you also need to have the float for world space light equals 0. Alright, so these ones here, if you're using Unity 4, they're already predefined for you. I'm just going to comment these out for now because we don't need them, but I will leave them in here for you guys using Unity 3.5. You can download this, you can uncomment them if you need to. Alright, so just if you need them, you can uncomment those. So what object to world does is object to world is a 4x4 transpose that we can multiply by our vertex position to convert it from object to world space. And we can also do the reverse and convert it from world to object space with the world to object transpose. And the world space light position is quite obviously the position of our light in world space. So this makes sense. It's fairly straightforward. If you've got any questions on that, feel free to let me know. Okay, so what we're going to do now is create our struts. Alright, so we have our strut vertex input and our strut vertex output. These don't change from shader to shader, so we'll type them out both and then we'll fill in the things that do change. We have float for vertex, the semantic position, and to use that in the output, we need to grab the float for pos SV position. Just as we discussed in the first tutorial, the position is just taking the position from our object to our vertex input so that we can then multiply it by the Unity matrix MVP. What happens then is we take that and we send it to the vertex output so that our GPU can send it back to Unity and we can actually display it. Alright, so the other one we need is we need to go float 3 cull, and we're going to, actually no, not on this one, we're going to have float 3 normal in this one. So we're going to grab those normals. Because we're actually using lighting now, we do need the normal direction, or the normal rotation I should say, and we're going to output a float 4 color, and I'll just give that the semantic of color. It doesn't really matter what semantic you give it. You can give it something like text code 6 if you like, but we'll just use a color. The color, by the way, contains the vertex color. So if you come up here and we could do something like float 4 color, that will grab the color from the vertices, so the vertex color, and it'll pass it to the vertex shader. Over here we are writing to it, so it's just going to overwrite the vertex colors with our own color. So hopefully that all makes sense. It's nothing overly advanced right now, but let's get into the vertex function. Alright, so this one here is going to be vertex output, vert, and of course vertex output O and return O. Alright, so we're going to be outputting to vertex output, so that's what we have here. We're going to use O as our vertex output, so O equals vertex output. Now we do that this way around instead of an equal sign, because it's not a float 4, it's a full-on class. The vert function has a vertex input which we're assigning to V, so that we can call the things in here with V. Fairly straightforward, we've discussed that in the last video. Let's move on. Alright, so what we need to do is start off with what we know. O.pos, so we're going to return the position. Just like before, we need to multiply the Unity matrix MVP with the v.vertex, and that will just make sure that we're outputting the right position for our vertices in a way that Unity can understand. And we also want to return a color. O.cull equals, but we don't know what we want to return yet. The only other thing that we can work with is the normal. So if we just go ahead and return the v.normal actually need to convert this to a float 4. So v.normal, comma, F1O. If we just return that, just so that we can see something, and come back into Unity, and it's not going to work at the moment. We just look through here, what we've got, undeclared identifier. We have no fragment program at the moment. So let's just go ahead and create one now, just so that I can show you what the normals look like. Alright, so this one here, we're going to go float 4, frag is going to be vertex output I, and in here, let's just go return I.cull. Alright, so there's still an error here. I've done it again. What we've got is I am missing a T. Alright, there we go. So there's little spelling mistakes like that that can cause little bugs. I'm going to leave in the majority of the errors that I make for the series. So when you're learning them, you will come across a lot of errors, and although at the end of the series we'll be covering all the errors you can come across, for now it will just help show you what's going on. Alright, so let's just close that, and you can see this is what the normals look like on our model. What we need to do is we need to work with these normals. Let's go float 3, normal direction, equals, this is going to be multiply the v.normal by the underscore world to object, just so that we can convert that one. To object, make sure it comes up in blue. Now of course world to object is a float 4 before, whereas normal is a float 3, it's only XYZ. So we need to create that fourth vector. Just go float 4, 0, because we're not using it. And then after this, we're just going to go .xyz. Alright, so that's just so that, because we're only using float 3, we need to put a .xyz, so that Unity knows which 3 components it's grabbing and which one it's getting rid of. Alright, so we load that, and it looks exactly the same. It's now in object space. You probably don't really notice it. It's one of those calculations that you have to have, but showing it as a color doesn't really show you why we have to have it. There is a lot of documentation on it. If you really want to learn more about why we have to have this, on the Unity documentation there's a bit of information about vector length and so on and so forth. At the moment, just understand that what we're doing is we are multiplying our normals by the world to object to get them into object space, and then we are taking the XYZ component. What we can also do, just to be safe, is we can normalize this I don't know if I've told you the normalize function yet, but what the normalize function does is it will squeeze all the values to between 0 and 1. Alright, so let's say you've got a value between -2 and 360. It will squish that to 0 and 1. That's what the normalize does. The other one that we'll often use is a saturate, and the saturate will just trim off everything that's not between 0 and 1. So if you've got something between -1 and 2, it will become 0 and 1. Let's move on, now that we've got that one there. So we can actually display this if we want. Alright, so change the little icon over there. You can't really see anything different here at the moment. What we need to do next is we need to calculate the light based on our normals. So if we just come through and create a couple more vectors here. There's float 3, light direction, and we need a float 10 equals 1.9. So we're not going to be working with attenuation just at the moment. And what we're going to be using eventually is when we start talking about point lights, we'll talk about fall off of light as the light gets further away from the object, and that's where attenuation will come in. So we're just going to leave this as a just a one variable now, so it's just so that you understand where it goes. Okay, so next up we need to calculate our light direction. So the light direction equals underscore world space light pos 0 dot xyz. Okay, so that one there is our light direction. Now once again we need to normalize this. So normalizing this will just bring it to that 0 to 1 range. It's not a biggie, but when you start to get rotations that aren't 0 to 1, well, they're not 0 to 1 anyways, you start to get a little bit of a funky effect going on. So that's why we normalize it, and it just reduces those artifacts. So on our simple scene at the moment you won't actually see any artifacts, so I won't bother showing you, but try it out on one of your scenes. If you take away all the normalizers, you'll see that things start to go a little wacky, and that's just what the normalizer is doing. It's just, you know, squishing things into the 0 to 1 range. Alright, so let's calculate the actual lighting. So float 3 fuse reflection equals, and let's just for the moment go dot normal direction light direction. Alright, so for the moment let's just use this one here and just show you what the dot product is doing before we add in colors and attenuation and so on. Let's reload that. Alright, so you can see how that's working. Now one thing I'm going to point out is you can see that the light direction here isn't actually affecting it. Now this took me a little while to figure out to start out with. I couldn't find any resources on it anywhere. And the problem is that we are working in a forward based light light mode, and we're not telling Unity to, or we're not telling our shader to do that. So up here we need to add in some tags. So tags contain things like what light mode you're working with. So we can go light mode equals forward base. Okay, so the other one is forward add when you're working with additive lighting. For this one here, because we've only got one pass, we're working with forward base, and these sort of help to blend our shaders together. So this is something that only really showed up in Unity 4 with the most recent update. Before then it didn't actually matter. That's why it kind of caught me off guard there. But by doing that, if we just reload this now you can see that it's working. Alright, so at the moment you can see that it's just a 0 to 1 range. It's actually 1 to -1. If we had some form of light on the other side, you would notice that it was subtracting from it. So this is actually 1 over here, and this is actually -1 over here. So we need to fix that. So what we're going to do is we're going to do a max 0.0 and this. So that there will truncate off the anything below 0. Now we could use the saturate function, but we actually don't want to do that because sometimes you get light that is more than 1. So if you use the saturate, you won't get those values, and they are very important, especially when you want to get those really bright highlights. Alright, so now that we've got that, we can save that, and we won't see any difference because we didn't have any other lights affecting this. Actually, you can see it gets a little bit softer around the edge actually. There we go. Okay, so what we want to do now is we need to colour it. So we're going to go attenuation, which is the distance from the light to the source, which at the moment is just set to 1 because we're only working with directional lights. I'm going to multiply this by float 3. Actually, we probably don't need to define this as a float 3. We can just go light colour 0.xyz. So that's the colour of the light. So if we just save that, you can see we can grab this now, and we can change the colour there, and we can also change the intensity, which is fantastic. Just take that back down. So what else we need to add in is the colour of the surface. So I'm just going to add that in here. Let's go times underscore colour dot RGB. So if we just come back into Unity now, we can now change the colour of this. So we can change the colour of that, and we can change the colour of the light to get some cool effects. So if you do red and blue, you'll get black. Really cool. Alright, so we now have diffuse lighting, and that is fantastic, isn't it? Alright, so there was a lot to go through, so I'm just going to go through this and just clarify each line for you and try and get that understanding cemented in. So our first line here is of course our name, and we have our properties block with our colour set to 1, and we've called it colour, and type is of course colour. Now we've got the tags. Now tags contain special information about each pass. For this one here, we're telling it that the light mode is a forward base, so we're using the forward rendering. And this here is something that you only have to add in the most recent version of Unity 4. So I can't remember what version I'm using at the moment. 4.0.0F7, and it's a professional version. So in this version here, I updated from F5, and it broke my shaders. So you now need to add in the tags of forward base. Alright, CG program. So we're going to stop programming in ShaderLab, start programming in CG. We're going to tell Unity where to find the vertex and fragment functions. Define our colour so that we can access it. Define our float for light colour 0 so we can use our light colour in our shader. And of course, Unity 3 definitions, we need to define the object to world, world to object, and world space light position 0. We didn't actually use the object to world, but we'll be using that in the future. These are actually already predefined in Unity 4, so we'll just comment them out, and if you're using Unity 3, just make sure that you uncomment them so that it will work. Right, we have our strokes, so we're going to grab our position and normal from the object information, and we're going to output the position and the colour. For our vertex function, we're going to assign these to vertex output struct. We are going to use vertex input as a base, and we are using V so that we can quickly access them, and outputting to O with the vertex output. For the normal direction, we are multiplying our normal by the world to object transpose, and the normalize there is just making sure it's in the right range. We'll define a light direction and attenuation. We don't worry about attenuation for now, it's just so that you know where it goes. We will be dealing with that a little bit later. The light direction, we are just normalizing the world space light position, just so it's in the 0 to 1 range, so that we can use it correctly. Then going to calculate our lighting, which is attenuation times the light color multiplied by our lighting pass here. So our dot product will calculate lighting from 1 to -1 based on the normal's direction to the light. The max will remove all the values less than 0, and the color, of course, tints it our color. Finally, we will then assign it to the color by using a float 4, so that we add in that fourth component, which is the alpha, which we didn't calculate up here. We then have the position, so outputting the position by multiplying our vertex position by the Unity matrix MVP, just so that Unity can understand it. For the fragment function, we are just taking in the vertex output and directly outputting i.color. So that is it. That is a Lambert shader. Let's go ahead and move on to the next part of this tutorial here. Alright, so the next part of our Lambertian shaded model is the ambient coefficient. And this is very easy. Unity has a built-in variable called Unity Light Model Ambient, which is a float 4 color specified by your project. Let's go ahead and add this into our shader right now. Okay, so I'm going to jump back into Unity now, and let's go ahead and just duplicate our little model here. And I'm just going to call this one here to B underscore ambient. Alright, so we're going to go ahead and duplicate our Lambert, and we're going to call this to B ambient. Duplicate our material to B ambient. Now I'm not going to make you guys watch me write this shader from scratch again, because it's basically the same. We're just going to be adding in a little bit of difference. We will be adding in just the ambient coefficient. Let's come down here into our diffuse reflection, and what we're going to do is add in our ambient lighting. So we're going to go and let's just get our color, and we're just going to remove the color from this equation right now. And this is diffuse, and what we're going to do is go float 3 light final equals diffuse reflection plus Unity light model ambient dot xyz. So what we're doing now is adding both of those lighting components together so that we can then multiply this by our color, which I'll just paste in down there. Now the reason we don't just add it on the end here is because it will effectively tint our color. We don't want it to tint our color. We want the lighting to be all calculated as once and then be used to light the model. So it's a very subtle difference, but when we're working with things where we need photorealistic lighting in our shaders, it's very important to make sure that the lighting itself is just there to blend how much of our texture is showing. If we had, for example, the back side of the model, and we had a textured model, it would show up that the back side was just a slight grey colour where the ambient lighting was coming through, and it wouldn't have shown any of the texture. So I won't show it on this model because you won't see any difference, but when we come to textured, go ahead and play around with that and you'll see the difference. Right, so that's that one there. I'm just going to rename this one here to be ambient. So let's save that one there. Into Unity, reload it. This one goes Unity cookie to beginner to be ambient. And let's just drag this over into this one. Alright, so what have we got? Ah yes, diffuse reflection. We need to make sure we use light final times color. Reload that, and there you can see we have a bit of ambient light. So this is the ambient lighting that is determined in render settings. There we go. Alright, so if you go into your edit render settings, you have this option here, and you can tint that to tint the model, which is pretty cool. So that's how ambient lighting works. Alright, so that brings us to the end of part 2. Hope you guys enjoyed this. If you guys have any questions at all, feel free to let me know. Remember that the presentation, if I just find that, where is it? There it is. Alright, so this presentation will be available in the source files along with a text version of this tutorial and the source shader files. So you're welcome to open them up and use them however you like. And that's it for today. My name is Alex Telford and you are on unitycookie.com.